Welcome back to QHSE Talks and to a new episode in our CSP series. In this series, we are not memorizing definitions just to pass an exam. We are building professional judgment, the kind of judgment that determines whether a workplace is merely compliant on paper or genuinely safe in reality. And today's episode is one of the most critical in that journey because we are stepping into Chapter 7, Toxicity. Here's the hard truth. Many safety failures do not happen because hazards were unknown. They happen because hazards were misunderstood. In our industry, people often say, this chemical is toxic, or this job is hazardous, but very few stop to ask, toxic to whom, at what dose, through which route, and over what time frame. When those questions are not answered clearly, risk assessments collapse, exposure limits are misapplied, and control measures become dangerously generic. Toxicity is not just a scientific topic reserved for laboratories or toxicologists. It is the foundation beneath industrial hygiene, occupational health, process safety, and even emergency response. If you misunderstand toxicity, you will misunderstand exposure. If you misunderstand exposure, you will underestimate risk. And when risk is underestimated, people get hurt, sometimes years later, long after the job is finished. Chapter 7 forces us to slow down and think like professionals. It reminds us that chemicals do not behave emotionally or subjectively. They behave according to dose, duration, and route of entry. A substance that is harmless in one context can be deadly in another. A small exposure today may seem insignificant, yet lead to irreversible disease decades later. This is why toxicology matters, not just for the CSP exam, but for real-world decision-making. In this episode of QHSE Talks, we are going back to the absolute fundamentals. We will strip away assumptions, clarify terminology, and rebuild understanding from the ground up. We will talk about toxicity as a science, toxicity as a property, and hazard as a function of exposure. We will explore why the phrase, "the dose makes the poison," is not a slogan, but a governing law of safety practice. This episode is not about fear, it is about clarity, because clarity is what allows safety professionals to design effective controls, communicate risk honestly, and protect workers in ways that actually matter. So let's begin at the only place that makes sense, the base science itself.
That makes perfect sense. Clarity of language is clarity of thought, especially in safety. So let's start with the absolute base science. Toxicology.
Right. So toxicology is defined as the science dealing with the study of poisons and their adverse effects on living organisms. It's an ancient field, really, but its modern application in the workplace predicting harm from synthetic compounds is relatively new.
And building directly on that, we have the term toxicity.
Toxicity. This is the measure of the degree to which a substance can cause harm to an exposed organism. And what's crucial here is that toxicity is an inherent property of the substance itself.
Okay, so it doesn't change based on the situation.
Exactly. Whether a barrel of cyanide is locked away in a vault or sitting out in the open on a factory floor, its high toxicity doesn't change. It's the material's DNA, so to speak.
So if something has a high toxicity, we generally just call it a poison.
That's the one. A poison is simply a substance that, when it's administered or introduced to an organism, is harmful. It's really the layman's term for a highly toxic substance. Now, for industrial hygienists, another term that pops up frequently is xenobiotic.
That one always sounds highly technical. What does it actually mean in the context of, human exposure?
It's a great question. A xenobiotic is defined as a substance found in an organism that is not normally produced or expected to be present in it.
So a foreign chemical.
A foreign chemical presence, exactly. Think about it. Almost all the chemical contaminants we worry about in the industrial world, solvents, heavy metals, synthetic organic molecules, they're all xenobiotics. This means the body hasn't evolved natural, robust ways to handle them, unlike, say, dietary sugars or naturally occurring hormones.
Okay, this is where the intellectual pivot happens, because now we have to distinguish between a hazard and a risk. This is arguably the most fundamental calculation a safety professional makes, and it's where the public I think often gets confused.
It is the safety professional's calculus indeed. The hazard is the inherent potential for a substance to cause harm. So, a stack of dynamite is a hazard. Concentrated hydrofluoric acid is a hazard. That inherent danger is constant. It just is.
But the risk, that's the dynamic part of the equation, the one we can actually manage.
Precisely. The risk is the measurement or the estimate of the likelihood that harm will occur. This is the fundamental insight. Risk is a function of both toxicity and exposure.
Risk equals toxicity times exposure.
That's the formula. Let's take that highly toxic hydrofluoric acid. If that acid is stored in a double-walled container in a secured, negatively pressurized vault, with employees required to wear full PPE and follow strict protocols.
A hazard is still incredibly high.
Right, the acid itself is just as dangerous. But the risk is low because we've controlled the exposure.
And conversely, you could have something far less toxic, maybe a simple industrial detergent.
Could pose a huge risk if a worker is routinely splashing it onto their skin, that's high exposure, without wearing gloves. That calculation risk equals toxicity times exposure is what allows modern industry to safely manage materials that are inherently dangerous.
So our job isn't to eliminate hazards, which are inherent.
Our job is to rigorously control exposure, and by doing that, we manage risk.
That clearly defines the mission. Okay, let's talk about quantifying the effect, starting with a timeline. How do we categorize the duration of an exposure?
We deal primarily with two types of dose timeframes in toxicology. First is acute exposure. This is short-term. We're talking seconds, minutes, hours, or maybe a few days.
And the effects are usually immediate.
Usually. This results in immediate visible effects, like a chemical burn or sudden dizziness or a rapid onset illness. It's cause and effect, very clear.
And then there's the more sinister type of exposure that safety managers often dread dealing with.
And that is chronic exposure. This is long-term. It spans days, weeks, months, or even years of low-level contact.
And the danger here is its latency, right?
That's the insidious part.
Yeah.
It leads to these slow-onset diseases, cancers, neurological disorders, chronic lung disease, which are often incredibly difficult to track back to a specific workplace event that happened 10 or 20 years prior. This is where biological monitoring becomes absolutely crucial. To even begin regulating these things, researchers have to define benchmark levels. You see these acronyms constantly in toxicological reports. NOEL, OAEL, LOEL.
These benchmarks are absolutely vital for setting what we call permissible exposure limits, or PLs. We have to start somewhere, and that somewhere is the NOEL, the no observed effect level.
No observed effect level. So that's the dose where absolutely nothing happens.
Correct. This is the highest dose at which no change whatsoever, no biological response at all is observed in the test population.
Then we get slightly more specific with the next level up.
That would be the NOAEL, or no observed adverse effect level. This is a subtle but critical distinction.
Okay, what's the difference?
This is the highest dose at which no adverse effect is observed. It means there might be a subtle biological change, maybe a slight shift in a blood marker, but it's nothing that would be classified as harmful or detrimental to the organism's health or survival. The body is reacting, but not being harmed. So if the NOAEL represents the highest safe dose that's observed in, say, animal testing, how do regulators translate that benchmark into a safe 8-hour PL for a massive, diverse working population?
That is the critical bridge, and it's a very cautious one. Regulators don't just use the NOAEL directly, they apply a safety factor.
A safety factor?
Yes, often a factor of 100 or even 1,000. This is to account for, first, species differences moving from animal models to humans, and second, for the individual variability within the human population.
So you're protecting the most vulnerable person, not the average person.
Exactly. You want to protect the most susceptible person in the workforce. So the regulatory limit you see, the PL or the TLV, is usually just a tiny fraction of the experimentally derived NOAEL.
That really contextualizes the safety margin. So below those levels we're okay, but above them, we start seeing trouble.
Yes. That's where we get to the LOEL, or lowest observed effect level, and the LOAL, the lowest observed adverse effect level. These markers tell us the exact threshold where detectable biological responses begin to appear, whether they are minor or serious.
So they help scientists understand the dose-response curve.
Precisely. They show how quickly the effect accelerates as the dose increases.
And finally, we have the ultimate measure of raw immediate danger, the LD50.
The LD50, the lethal dose, it is defined as the amount of material, typically liquid or solid, often expressed as milligrams per kilogram of body weight, that is required to cause death in 50% of the exposed test population.
So it's a blunt instrument, really.
It is. This metric allows for a rapid comparison of the raw acute lethality of chemicals. For example, comparing the LD50 of common table salt to, say, botulinum toxin illustrates the vast, almost unimaginable difference in inherent toxicity.
But, relying on LD50, which is derived from animal testing to determine a lethal dose, it feels a bit crude in the context of modern workplace safety standards, which are focused on chronic low-level effects.
That's an excellent point, and it's absolutely correct. While LD50 is a foundational metric, it's rarely used today to set occupational exposure limits like the 8-hour time-weighted average. It measures acute, high-dose lethality.
So what do we use instead?
Modern toxicology prioritizes chronic endpoint studies. We're looking at carcinogenicity, neurotoxicity, reproductive harm, which all require the NOA, UL, and low AL data derived over much longer periods of exposure. The goal is to prevent long-term illness, not just immediate death.
Okay, so we understand the essential language and how toxicity is quantified. This really is the intellectual foundation for everything else we're going to discuss.
Now that we have the language, we have to understand the mechanics of entry. Toxicological harm requires a hazard, yes, but equally important, it needs a route for that hazard to breach the organism's defenses.
And there are 4 primary and critical pathways or routes of entry through which hazardous substances get into the body. These are inhalation, ingestion, absorption through the skin, and then percutaneous or intravenous injections.
And while absorption through the skin can often be the largest cumulative exposure pathway over time in certain industries, like, say, agriculture,
Right.
we really need to focus extensively on inhalation. In industrial settings where you have fine dusts, mists, or vapors present, inhalation is often the fastest and most dangerous route.
Why is that? Why is the respiratory system such a uniquely efficient and, I guess, vulnerable route of entry?
It's entirely due to the evolutionary physiology of the system itself. The respiratory tract is designed for one thing: maximum rapid gas exchange.
It's a giant surface area.
A massive surface area. It runs from the nose and nasal passages, through the mouth, down the pharynx, larynx, trachea, bronchi, and finally into the deep lung, the alveoli.
And that anatomical structure is basically a massive high-speed interface between the external environment and our internal bloodstream.
Precisely. Consider the surface area. If you could flatten out all the thousands and thousands of tiny air sacs, the alveoli, they would cover the size of a tennis court.
A tennis court, wow.
A tennis court. And why is this critical? The alveoli are enveloped by a vast network of capillaries, these tiny blood vessels. This extreme proximity means that as the air, including any toxic gas or fine particulates, enters the alveoli, the molecules can permeate the ultra-thin alveolar membrane directly into the bloodstream.
So it's a direct, unfiltered shortcut to the circulatory system.
It's the express lane. Oxygen moves in, carbon dioxide moves out, and unfortunately, highly soluble toxic gaseous molecules or very fine particles, especially those less than 1 micron, travel right along with the oxygen.
And they bypass the liver.
They bypass the liver's first pass detoxification. They go straight into the bloodstream for distribution throughout the body and to all the vital organs.
The body does fight back, though. It's not completely defenseless. What are the natural defenses trying to stop these foreign bodies before they reach the deep lung tissue?
Our initial defenses are actually quite clever, and they're concentrated in the upper respiratory tract. First, you have the mucus lining the nose, the sinus cavities, and the bronchial tubes. It acts like sticky flypaper, trapping larger particles.
Okay, so it traps them. Then what?
Then this mucus escalator system works to expel the trapped particles, usually through sneezing or coughing.
And the mechanism that actually drives that escalator, what pushes it up?
That would be the cilia. These are tiny, hair-like projections that line the airways. They beat in this coordinated wave-like motion, constantly pushing the layer of mucus, along with any captured contaminants, up and out of the lungs towards the throat.
Where it's either swallowed or spit out.
Exactly. And these mechanisms are excellent, but they're excellent at capturing larger particulates, things over about 5 microns in size.
But those defenses, while they're ingenious, they can be completely overwhelmed, particularly if the volume of air being processed increases dramatically or if the particle size is too small.
Correct.
And this brings us back to a crucial point you raised earlier about tidal volume and physical activity.
This is perhaps the most strategic yet often overlooked factor in industrial hygiene risk assessment. Let's think about it. In a normal, relaxed state, say, you're sitting at a desk, a person breathes about 10 to 14 times per minute.
Okay, pretty slow.
Right. This moderate rate results in an air intake of roughly 4.3 to 5.7 liters of air per minute. That is our baseline risk for calculating a time-weighted average.
But the reality of so many industrial jobs involves intense, heavy labor. You think about maintenance workers, emergency responders, or anyone doing high-speed production work.
That changes the entire equation, fundamentally. As physical activity increases, heavy lifting, shoveling, climbing ladders, even just working at an accelerated pace, the body's metabolic demand for oxygen skyrockets.
So you breathe faster and deeper.
Much faster and deeper. The respiratory rate can accelerate up to 1 breath per second, and this amplified rate leads to a total air intake, or what we call tidal volume, of up to 120 liters per minute.
Wait, say that again? From 5 liters to 120.
Up to 120 liters per minute. If we compare the relaxed baseline of around 5 liters per minute to the intense 120 liters per minute, that is an increase by a factor of 24.
24 times. That's not just a statistical anomaly, that is a physiological risk multiplier.
It's a multiplier that fundamentally challenges how we think about the time-weighted average, the TWA. If a chemical exposure limit is calculated based on an 8-hour TWA, meaning it assumes an average breathing rate over the day, the instantaneous dose an employee gets performing high-intensity work for even a short period, say 30 minutes, can be massively higher than that TWA suggests.
Because they're inhaling 20 times the volume of contaminated air in the same amount of time.
Exactly. So an employer might feel compliant because their 8-hour TWA monitoring results are below the OSHA-PEL, but during that actual heavy labor segment, the worker is experiencing a dangerous, instantaneous spike in their exposure.
So the TWA provides regulatory compliance, but it might fail to provide biological protection during those peak work demands.
That's the risk. This necessitates specific controls, things like forced rest periods, task rotation, or localized exhaust ventilation, placed directly at the source controls designed to account for those instantaneous peak doses, not just the daily averages. You have to manage the intensity of the dose, not just the duration.
That completely shifts the risk management perspective. Now let's quickly address the other routes of entry.
Sure. Ingestion is a standard route, though often unintentional. This happens when contaminants are swallowed, typically from contaminated hands, food, or water, or when workers eat or smoke in contaminated areas.
And the body has some defense there.
It does. Many ingested toxins are partially neutralized or metabolized by the gastrointestinal tract and the liver, but others, like lead or certain pesticides, are readily absorbed.
And absorption via skin contact.
Dermal absorption is very often underestimated. Substances can permeate through the protective layers of the skin right into the bloodstream. Many organic solvents, phenols, highly lipid-soluble heavy metals, they can cross the skin barrier rapidly without causing any visible irritation.
So they're silent systemic threats.
They are. Proper gloves and protective clothing are absolutely non-negotiable for these materials.
Finally, percutaneous and intravenous injections.
These are routes where the barrier of the skin is either intentionally or accidentally bypassed. In an occupational setting, we're primarily talking about the accidental scenario.
A needle stick injury.
Right. A needle stick in a medical or research lab, or a high-pressure injection injury, which is common in hydraulic repair. This route is extremely dangerous because it provides an immediate, undiluted dose directly into the systemic circulation, bypassing all the external defenses we just discussed.
It's a catastrophic failure of the defense system.
It is.
So we've established how the poison gets in. Now we dive into the internal battle, what happens chemically and biologically once that xenobiotic reaches the tissues. We have to start by reinforcing the foundational concept that governs all of toxicology, the dose-response relationship.
This is the bedrock of the entire field. The principle that increasing the dose increases the effect. It's also known as the exposure-response relationship. It describes the change in effect on an organism caused by differing levels of exposure, from the NOEL all the way up to the LD50.
It sounds like a linear relationship, but the body has ways of trying to mitigate the damage initially, right? It's not a straight line up.
It's not. The body possesses a detoxification toolkit, primarily in the liver, and its capacity to withstand exposure is what we call tolerance.
How does tolerance work?
It occurs when the organism adapts, perhaps by increasing the synthesis of certain enzymes in the liver that are designed to metabolize and excrete the substance. However, tolerance is a temporary or limited capacity. If the dose or duration overwhelms that detoxification pathway, tolerance quickly breaks down, leading to rapid accumulation and adverse effects.
And when we talk about chronic occupational exposure, a critical factor for safety monitoring and, frankly, for legal cases is the concept of the latency period.
The latency period is absolutely central to occupational health litigation and epidemiology. It is the time delay, which can span months, years, or even decades between the initial exposure and the actual onset of clinical symptoms.
So things like mesothelioma from asbestos or chronic beryllium disease.
Exactly. Those are the classic examples.
That makes establishing causation incredibly difficult.
It's the greatest challenge. A worker might have had a high-level exposure incident 20 years ago, but the illness only manifests today. That makes it nearly impossible for a safety professional or a doctor to definitively link the current illness back to a specific workplace event in the past. It requires meticulous record-keeping and historical monitoring data.
Now, poisons are often categorized by where they attack the body. A simple yet effective classification known as target organ toxicity.
This classification helps us prioritize our efforts, both medical surveillance and engineering controls. The three major systems we track are the liver, the kidneys, and the nervous system, simply because they are either detoxification hubs or are extremely sensitive targets.
Let's start with the liver, the body's workhorse.
Hepatotoxins. These are chemicals that primarily target the liver or blood. The liver is the body's major metabolic and detoxification center. It's responsible for converting fat-soluble xenobiotics into water-soluble forms that can be excreted.
So it sees everything.
It handles virtually everything that enters the circulation. Because of that, it's highly vulnerable to chemical damage from things like carbon tetrachloride or vinyl chloride.
And the kidneys, the body's filtration system.
Those are targets for nephrotoxins. These are agents that adversely affect the kidneys. The kidneys filter enormous volumes of blood, about 180 liters a day, concentrating toxins and metabolic wastes before excretion.
So the concentration process is the danger.
That's the problem. That process makes the kidney tissue itself vulnerable to damage from heavy metals like cadmium and mercury, which can accumulate and cause kidney failure.
And finally, the most complex and delicate system, the neurological one.
That's the target of neurotoxins. These agents cause adverse effects on the nervous system, the brain, the spinal cord, and the peripheral nerves.
Why is the nervous system so susceptible?
It's susceptible for two reasons. It's highly lipid-rich. The myelin sheaths around nerves are essentially fat, and it has a very high metabolic demand for oxygen and nutrients. So lipid-soluble toxins like elemental mercury vapor or certain solvents can easily cross the blood-brain barrier and cause devastating, often irreversible damage. We'll see this mechanism later when we discuss mercury.
Shifting now to one of the most feared and studied long-term biological effects, cancer. We need to go step by step through the 4 stages of carcinogenesis, the mechanistic progression of malignancy.
Understanding these stages, initiation, latency, promotion, and progression, is crucial because it shows us exactly where we can potentially intervene to prevent disease, even after the initial exposure has already occurred.
Okay, so where does the process begin? The first step.
It starts with initiation. This is the starting event. It's the moment the cell's genetic material, its DNA, is permanently damaged.
Like a typo in the genetic code.
A permanent typo. This damage often occurs through the formation of what are called DNA adducts, where a chemically active metabolite of the xenobiotic binds covalently to the DNA strand, altering the sequence or structure. This is usually a rapid, irreversible change caused by a genotoxic carcinogen.
After that initial defining event, there is often a deceptive calm.
Right. That's the second stage, the latency period. As we discussed, this is the often lengthy interval between initiation and the subsequent stages. The initiated cell, though damaged, may remain dormant, or its growth may be suppressed by the body's defenses for years or even decades before it divides abnormally.
Then at some point, the dormant problem begins to multiply.
That's promotion. In this phase, cell growth is actively encouraged. Promoters are typically agents that don't damage DNA directly, but they stimulate the initiated cell to divide rapidly, or they suppress the body's natural cell death mechanisms, a process called apoptosis.
So they're not the ones causing the typo, but they're hitting copy-paste over and over again.
That's a great analogy. This rapid division gives the initiated cell a huge selective advantage, accelerating the formation of a mass or a tumor. Examples of promoters could be chronic irritation or certain hormones.
So if you remove the promoter, you can stop the process.
In many cases, yes. Removing the promotional agent, even after initiation has occurred, can often halt or even reverse the process.
And the final transformation into full-blown cancer.
That is progression. Progression refers to the transformation from a localized, potentially benign tumor into a neoplasm and ultimately to full malignancy. This involves the acquisition of more mutations, giving the cell the ability to grow uncontrollably, invade adjacent tissues, and then metastasize spread to distant organs.
If cancer is initiated by DNA damage, by that typo, how do toxicologists identify potential initiators or mutagens before they cause harm in humans? That's where the predictive tool, the Ames testing, comes in.
Right. The Ames test is a brilliant, cost-effective, and rapid screening procedure designed specifically to determine whether a chemical is a mutagen, a substance that causes changes in the genetic material of an organism.
And the critical reason this test is so foundational to safety standards is its predictive power.
Absolutely. The crucial insight is the high correlation, not perfect, but very high, between a chemical's ability to mutate bacteria and its ability to cause cancer in animals and humans.
So if a chemical scores positive in the Ames test,
It is immediately flagged and treated as a highly suspicious potential carcinogen. It would require extensive further testing and, in the meantime, stringent workplace controls.
let's delve into the mechanics, because it's a very clever use of microbiology.
It really is. The test uses a specific strain of bacteria, Salmonella typhimurium. Researchers have engineered this strain to be defective. It carries a point mutation in the genes required to synthesize the amino acid histidine.
So it can't make its own food, essentially.
Exactly. Because it cannot produce histidine, which we abbreviate as HIS, it cannot grow in a culture medium that is histidine-free. It's histidine-dependent.
So if you put these dependent bacteria onto a histidine-free plate, they should all die, unless something fundamentally changes their DNA.
Correct. When the suspected chemical, the potential mutagen, is introduced, if it is mutagenic, it may cause a reverse mutation in that defective gene. It fixes the typo.
And that restores the bacterium's ability to make its own histidine.
Right. The bacteria that successfully revert, that mutate back to normal function, are the only ones that can then grow on the histidine-free medium. We just count the resulting colonies. The more colonies that grow, the more potent the mutagenic effect, and the higher our suspicion of carcinogenicity.
But wait a minute. Many industrial chemicals are not genotoxic themselves. They only become damaging once the human body tries to metabolize them. How does the Ames test account for the body's internal chemistry?
That is the most important technical detail of the Ames test, and it's what elevates it beyond a simple bacterial assay. To simulate human metabolism, researchers add a component called S9.
S9, what's that?
S9 is a microsomal fraction derived from homogenized rat liver tissue.
So you are literally adding a tiny bit of rat liver to the bacteria.
Precisely. The S9 fraction contains the necessary enzymes, particularly the cytochrome P450 enzymes, that the liver uses to metabolize foreign compounds. Many compounds, we call them procarcinogens, are only converted into their active DNA-binding mutagenic forms after they have been processed by the liver.
So the S9 mix ensures the test identifies these latent mutagens as well.
Yes, making the predictive screen much more comprehensive and relevant to human exposure. This ensures that chemicals like benzopyrene, which are harmless until metabolized, are correctly flagged as hazardous.
That technical detail completely changes the application of the test, moving it from a simple bacteria screening to a powerful predictor of human cancer risk.
Having covered the science, the lexicon, the routes, and the biological mechanisms, we can now apply this knowledge to some real-world industrial poisons. We're moving from the abstract principles to the exact, challenging controls required to manage 3 agents that embody very different toxicological risks.
Let's start with berylliosis and beryllium, which exemplifies an extremely low-dose, high-latency immunological hazard.
Right. Beryllium is a silvery white, lightweight metal. It's prized for its strength, its low density, and its high melting point. It's essential in high-performance applications.
Like aerospace.
Exactly. Used in lightweight alloys, especially in valves, electrical components, and specialized parts for the aeronautical, space, and nuclear industries. But handling it requires extreme caution.
The disease berylliosis, or chronic beryllium disease, CBD, is a serious, debilitating lung disease resulting from inhalation. And the core toxicological insight here is that all beryllium compounds should be considered potentially harmful if inhaled, even in just minute quantities. What makes it so unique and so dangerous?
Beryllium isn't just a straightforward chemical toxin, it's what we call a sensitizer. In susceptible individuals, exposure triggers a complex, cell-mediated immunological response.
So the body attacks itself.
In a way, yes. The body's immune system misidentifies the beryllium particles as a chronic invader. This leads to the formation of granulomas, these tiny inflammatory nodules in the lungs. It's an allergic immunological battle waged in the respiratory system, often years after the exposure even occurred.
That explains why the regulatory limits are so incredibly strict.
They have to be. They reflect this extreme potency and the long latency. The OSHA permissible exposure limit for beryllium is set at an almost unbelievably low level, 2.0 micrograms per cubic meter.
Micrograms, a millionth of a gram.
A millionth of a gram averaged over an 8-hour TWA. That kind of limit forces safety professionals to utilize extremely sensitive, often continuous monitoring equipment. You can't sample this with old, low-tech methods.
And there are even tighter limits for short-term exposure.
Yes. There is a ceiling limit of 5 micrograms per cubic meter, which cannot be exceeded for more than 30 consecutive minutes in a shift, and a strict, never-to-exceed limit of 25 micrograms per cubic meter.
Why so strict?
Because these limits are in place, because even low intermittent exposures can still initiate the sensitization process in susceptible individuals, leading to CBD years down the road.
The illness itself manifests in two distinct forms, though one is, thankfully, much rarer now.
Chronic beryllium disease, or CBD, is the primary concern today. It occurs from inhaling dust or fumes from beryllium products. CBD usually has a very slow, insidious onset, often with a long latency period, sometimes 5 to 40 years.
And it's personalized.
It is a personalized risk. Because it's an immunological disease, even very small amounts of exposure can cause the disease in people who are genetically susceptible and become sensitized.
And the acute form.
Acute beryllium disease has a much quicker onset, with symptoms resembling acute chemical pneumonia or severe bronchitis. This form is now very rare in the U.S., precisely because it was associated with massive exposures well above the current PLLs.
So the regulations worked for the acute form.
They did. The fact that we have mostly eliminated the acute form demonstrates the effectiveness of drastically reduced exposure limits, but the chronic disease remains a persistent, latent risk.
Next, let's transition to manganese exposure risks, which highlights neurotoxicity tied to specific industrial activities.
Manganese is an essential trace element for us, but excess exposure, usually via inhalation of dust or fume, leads to serious neurological damage.
Where do you find these high-risk exposures?
They're widespread in heavy industry. You see them in the machining of manganese alloys, the mining or crushing of manganese ores, using ferromanganese in steel alloy production, and most commonly today, using manganese-containing welding rods. Welding fume is a primary vector for exposure.
What specific neurological harm does manganese cause?
The primary chronic illness is called manganism. This is a severe, debilitating neurotoxicity that affects the central nervous system, particularly a region called the basal ganglia, which is responsible for motor control.
So the symptoms would be what? Like Parkinson's disease?
They often mirror those of advanced Parkinson's disease, tremors, difficulty walking, a masked or frozen facial expression, and general rigidity.
So it's often misdiagnosed as Parkinson's.
It can be, but manganism often presents with psychiatric symptoms earlier on, things like irritability, mania, or bizarre behaviors. It's sometimes called manganese madness before the full motor symptoms develop.
And is the treatment the same?
No, and that's crucial for medical professionals to recognize. Unlike Parkinson's, manganism is primarily associated with inhalation exposure and typically does not respond well to the standard Parkinson's drug, LDOPA.
What are the controls placed on this?
The OSHA 8-hour PAL for manganese dust is set at a ceiling of 5 milligrams per cubic meter for the total dust. This limit is significantly higher than that for beryllium, reflecting the different mechanism of harm and the dose required to trigger systemic effects.
But there's some debate about that limit.
There is. The American Conference of Governmental Industrial Hygienists, the ACGIH, sets their TWA much lower at 0.02 milligrams per cubic meter for the respirable fraction, which emphasizes the ongoing debate about the adequacy of the OSHA standard for preventing chronic neurotoxicity.
Finally, we must discuss mercury-related illnesses, focusing on differences in its forms and the most common route of occupational poisoning.
Mercury is one of the classic industrial poisons, recognized for its potent neurotoxic effects. Its key chronic health effects are peripheral neuropathy, so numbness, tingling in the extremities, and severe neuropsychiatric disorders, often presenting as tremors, memory loss, and behavioral changes.
The primary risk pathway is crucial to understand here, and it differs from the ingestion scares we hear about in environmental news, like with tuna.
That's right. While the general population often worries about organic mercury or methyl mercury in fish via ingestion, the primary occupational poisoning concern is the inhalation of elemental mercury vapor.
The shiny liquid metal.
Exactly. The shiny liquid metal you see in old thermometers readily vaporizes at room temperature. This vapor is highly lipid soluble, allowing it to easily cross the lungs into the bloodstream and, critically, cross the protective blood-brain barrier to target the central nervous system.
So a small spill of liquid mercury is actually an acute, ongoing airborne threat until it's perfectly cleaned up.
It is. The key prevention strategy is immediate, rigorous cleanup and reducing the temperature of the area to suppress vaporization.
And where are the high-risk workplaces for this?
They reflect the widespread historical and current use of mercury, extracting mercury ore, fabricating measuring devices like manometers or specialized thermometers, manufacturing and repairing fluorescent lights, manufacturing or using mercury dental amalgams, using mercury to extract gold, which is a major source of poisoning in artisanal mining globally, and working in the mercury cell room of a chlor-alkali plant.
And the regulatory requirements for this airborne neurotoxin.
OSHA sets the 8-hour TWA-PAL for mercury vapor quite low, at 0.01 milligrams per cubic meter, with a ceiling limit of 0.04 milligMRO. Monitoring has to be continuous and very sensitive, as mercury vapor is odorless and colorless. It's a silent invader of the respiratory tract.
And when you compare this to the manganese limit, you really see the toxicological ranking in action.
You do. Mercury's mechanism of neurotoxicity is potent enough to require limits that are 1,000 times lower than for manganese dust.
This section really ties together everything we've discussed. The neurotoxin targeting the nervous system, the inhalation route providing the shortest path to the brain, and the chronic dose leading to these long latency disorders.
What's fascinating here is the sheer spectrum of toxicity we've covered, from the massive volume of a non-toxic liquid required for an LD50, all the way down to the micrograms of beryllium capable of triggering an immunological response decades later.
It's a huge range.
It is. We have successfully moved from the broad concepts of hazard and risk to specific regulatory figures and detailed physiological responses. It really proves that successful safety management is ultimately applied toxicology.
And understanding the 4 routes of entry, and specifically that 20-fold amplification of your respiratory intake, that tidal volume during heavy work, gives you immediate, applicable, tactical knowledge.
It does.
You can see why a safety plan needs to account for not just what chemical you are working with, but how fast you are breathing while you do it. If you have employees performing intense, high metabolic work in an area with airborne contaminants, the instantaneous risk is fundamentally decoupled from the 8-hour TWA.
The application of this science is what moves the safety profession forward. It allows us to analyze not just the chemical makeup via the SDS, but the entire physical context and the human factor of the job itself.
So this deep dive showed that your respiratory intake, your tidal volume, can surge from roughly 5 liters per minute up to 120 liters per minute when activity level rises dramatically. Since occupational exposure limits like the time-weighted average are regulatory minimums averaged over 8 hours, we have to ask this final question.
Go ahead.
How profoundly does the intensity of work, the sheer pace of production, change the true instantaneous risk profile for an exposed employee, even when the 8-hour TWA is technically met? Is that TWA truly protective during peak periods of physical exertion, or does it merely confirm compliance on paper? This is a fundamental question of toxicology and work design that you must continually mull over as you assess real-world risk in your own environments.